Hello and welcome. This video is about metals and alloys, and we're going to look at a couple of details of the atomic structure in metals, and we're going to see how that affects some of the features of the metal itself. We're also going to look at how alloys can help change the features of metals, and we're going to look at something called shape memory alloys as well. Now, to begin with, if we were to take a pure metal, this one is an example of a pure metal, perhaps something like iron, and if you were to magnify a certain part of it, you might see the atoms arranged a little something like this. It's probably important to point out here that if we magnify to the size that I've shown here, you'd have to actually increase the size by many millions of times in order to see the atoms. But I've drawn a few here so you can see, and what you'll notice is that the atoms are arranged very neatly in rows and columns. Okay, so very neat, very straight rows and columns, and that means because they are in this structure, they can actually slide past each other reasonably easily. So if I was to take a hammer and apply some pressure, say from this direction here, so if I was to bang away at this piece of metal from this direction, what would happen is these atoms would actually slide past each other, and each time I hit it, they would move a little bit. This means that metals can be quite easily hammered or bent into shape. The word I think we actually often use is malleable. So we say the metal is quite malleable, but that just means it's easily hammered or bent into shape, and the reason for that is the fact that the atoms are in very neat rows and columns. In actual fact, if you were to take a sharp point as well, you could probably bang in between the point there and you'd see these slide away as well. Okay, so key thing there, metals can be hammered and bent into shape quite easily, and that's because the atoms are in very neat rows and columns and they're able to slide past each other. Now sometimes we want our metals to be much harder than they are in their pure state, and so what we can do is we can actually make what we call an alloy. And an alloy is a mixture of metals. Now we make alloys for various reasons. It might just be to change the color or to change a property like that, but we often make alloys to make the metals much harder. And what we see when we make the alloy is that the structure of these atoms is changed. So here's an example of an alloy that I've made, and if we were to look at the atoms in this particular alloy, which is much harder than the original metal, if we were to look at a bunch of atoms, oops, let's bring that to the front. If we were to look at a bunch of atoms there, you might see they look a little something like this. Now I have my original atoms that I've drawn from my first metal here, but I've also mixed it with these little atoms of a second metal. Okay, and what you can see is that the second metal, the atoms are actually disrupting the shape or disrupting the nice neat rows and columns. So we no longer have any nice neat rows and columns. So if I was to take my hammer from previously and try and bang from this side, you can see these atoms are in the way of the other atoms, and they're not allowing the atoms to slide and move as easily. So as a result, this metal is much harder. Now what you should be able to do is to be able to explain that, and it's really to do with how neatly these are arranged in rows and columns, and how a second material or a second metal can disrupt those nice neat rows and columns. Okay, so that's the idea of metals and how we can harden them. Another thing I want to go through with you is this idea of shape memory alloys, and one example of this is something called nitinol, and this is a alloy made from nickel and titanium. And it has a very special property in that it can be bent and changed in terms of its shape, but it has a special property that when you warm it up, it will go back to its exact original shape that it was in. So I could take this wire that I've made into this word smart for smart material, and I could deform that shape and make it into any other shape I wanted, but in fact I have to mention, you cool this down first. So you cool it, bend it into any shape you want, and then when you warm it up again, it slowly starts to go back to its original shape. Now that's quite difficult to show on a video like this one, but if you do a little search, you can probably see, in fact you can see lots of examples of this actually in action. It's actually quite fascinating to watch, seeing a metal bent out of shape, warmed up, and it goes back to the exact shape it was before. But you can do that after you've watched this video. Now one use of this is to perhaps used to make dental braces. This is supposed to be some teeth that we're looking at from above, and here is our nitinol brace, and what we can do is we can cool it down, wrap it around the teeth in such a way that we want, and then when we warm it up, or in actual fact when the warmth of the mouth gets to it, it will start to try and get back to its original shape, and that will cause the brace to apply pressure on the teeth, and that will put the teeth back into their, or not into their original position, but it will move the teeth into a better position than they might be already. And the great advantage of this is that it applies even pressure all the time. So this is braces, dental braces. Okay, so that's one use. Another use I've seen for this is in broken bones. We've got a bone that's been quite badly broken here, and the quickest way to make it heal is to apply pressure to it and squeeze the bones together so that they grow back into their original state they were beforehand, i.e. unbroken. So we can use, again, something like nitinol. We can cool it down, we can perhaps cut it open or wrap it around the bone in some way, like so, and then the warmth from the body will cause that to return to its original shape, which will contract around the bone, apply a lot of pressure, and hold those two bones together. Now the good thing about this is that the pressure is constantly applied. Normally before this kind of this kind of technology, the surgeons had to screw metal plates in there, but that didn't apply even pressure all the time. With this way, the pressure is applied evenly all the time, constantly applied on the bone, and it heals much more rapidly than it would have done previously. Okay, so we've just gone through some details about metals and their structure, looked at smart alloys. That shouldn't say metal, that perhaps should say I don't know what, but gone through a couple of examples, and hopefully that made some kind of sense. Thanks for watching, and I'll see you again soon.